Am I audible?
Yes, sir, you're audible.
Okay. So let's start. So there was some issue regarding my screen sharing, so I have to do still my. Perfect. I hope my screen is also visible. Any questions so far before we start? Anything? Any questions? Uh, any queries, concerns, clarifications? Huh? So are we good to go?
Yes, sir.
Okay. Now, yes, so let's understand what we were doing till now and try to connect what we are going to do next. Okay. So we were starting with, we were trying to do process control for which we require model. Huh? So we understood that the normal modeling might not help us. In the sense that uh, we require model. That's the key. Because we need to go and we cannot go and test things directly. So we need a model to play around. So the model traditional models are what? ODEs or PDEs. So that we found a problem because if you are having an ODE or PDE, then also it's a problem. So really speaking, why that's a problem in the sense that because they are difficult to handle. Mostly they are difficult to handle. So what we did was to get away with this, we try to do a Laplace transform. Okay, then converted to what is known as transfer function. I think there is still a lag. I have written everything on my screen and it's still not. I hope it is. You're not. So you're still saying the Laplace T, right? Nothing beyond that. Hello. Can someone say? Hello.
Yes,
Am
sir.
I audible to you?
Yes, sir,
Sir.
you're audible.
So what is that you can see on my screen? Laplace transform or beyond that?
So we can also see transfer function.
Only that much, right? So there is a huge, there is a lag. So let me just unshare and reshare my screen. Give me a minute. Bad network quality. Uh, let me just unshare. Stop presenting. Come on. I hope you are unable to see it. You are not able to see anything. Hello.
So the screen is visible and we can see till transfer function.
Maybe let me just log out and log in. You give me. Yes, at least. I hope you could see my screen.
Yes,
Yes,
sir.
sir.
Right.
Okay, so we were trying to understand the pipeline. Okay, so we had the model. We need to do control. So we had the model. Then we realized that the model that traditionally available is not really useful to us. So we could convert them into this nice Laplace transform, and that would yield something known as transfer function. And we have seen some examples of transfer function. That's where we were. Okay, so now as a natural extension, so we now zoom in more here. So we will just kind of take a lens and zoom in more on what are the type of transfer function that you would like to look into. So then, of course, as how do you look at the simplest one? So again, so we'll start with the simplest transfer function, which is like a first order system. Okay, then we will slowly go to second order system. Okay, and we will, okay, so this would be as part of this particular module. Then later we will look at higher order system of importance to us. So there may be many higher order systems, but the higher order systems that's of interest to us is what we will learn. So, so now we are now going to look at this aspect. So the interest first and second order system, that's what we are going to do. Okay, so now before we do that, let's understand some standard. Okay, let's try to see. So first order system essentially means that the transfer function is first order. What do you mean by that? So we have seen the first order transfer function. Order of a transfer function, order is the order of denominator polynomial. Polynomial, just a second. Order of denominator polynomial. So polynomial, what is the variable of the polynomial, which is in S? So your polynomial is the variable of the polynomial is S, and we are going to look at the order of that. So first order system, okay. So we are going to see this. You see that it is tau s plus one. Tau is a constant, of course. One is a new number, and denominator you have a constant, which is we call it as the gain. So any transfer functions of this particular form is first order. So similarly, again by definition, second order system. Second order system, okay. Like what would be the denominator polynomial degree should be 2, of course, tau square. Again, tau is constant, tau square square, and 2 theta. So we'll see why the theta and all is coming in here later. But you should see that it is a broadly like a form of a square s plus bs plus 1. So tau square is your a, 2 theta tau is your b, and 1. And of course, a denominator and numerator constant. You can also kind of factorize it and write it as product of two first order terms. That is what the first thing says. So see, this is a factorized form of the second order system. This is basically what you call as factorized form of two first factorized form of second order system as two first order system. Because we have seen last time, okay, we have seen a case where you have two tanks, and we have added, so there is a flow coming in here, and that flow is going to the second tank, and finally it gets this. And let's say Qi, then this is Q or naught. So if you develop a model between Qi and Q naught, this would be so we have seen that individual first the tank exit dynamics are first order. We have developed the transfer function for that, and we integrate them together. This would be second order. So this is like two second order, first order systems connected to each other. So similarly, that's why I told most of the cases you should be able to factorize them and write. Any doubt here? Any question? Each of them here would have a transfer function of 1 by tau s plus 1, k1 by tau 1 s plus 1, k2 by tau 2 s plus 1. So basically it is a factorized form. Any questions here? Any questions? May I go ahead? Okay. So then, okay, so this is the basic premise we would like to operate, and also we would like to see our, we also need to know what, yeah. So somebody was asking some question.
No, sir, it's just saying that.
Okay, perfect. So other things that you would like to hear, let's say, what is our system transfer function y of s, output by u of s. Assume that, let's say, it's a first order transfer function. First. So this is the standard transfer function form, y of s by u of s. It will come, it's slightly, so y of s by u of s is equal to k by tau s plus 1. I can see out, so we are interested in this output. This is y of s, and it may be in the time domain y of t. Fine, and this is subject to the inputs that you provide to this u of s. So u of t or u of s in the s form, they dictate the output y of t. See, it's like this, okay? So you have a reactor, you are feeding again something, and you are taking it out. This is F, I, F naught, maybe concentration here. And let's say you are interested in again. So consider the case you are also have a heater. This is the same example that we know. So we are interested to, let's say, look at the outlet temperature T or not, and this is Ti, and this is the Q. So we are, of course, our final variable is output is T naught. Okay, input, let's say, is there are two inputs actually, Ti and Q. They are the inputs, and we would like to see how the output is varying with respect to, this is input in the sense these are input variables. They are not really the inputs, right? So they are the placeholder names. So inputs could be anything. So the inputs that you can see here is what some sample input is what you really see over here. So what is that? So the inlet temperature variation, maybe the heat input variation could be a step. So this is a step change. It essentially means that, so many lot of time you did not give an input, then you suddenly changed it and you kept it constant. Second. So heater, for instance, it's like heater off for a long time, and at that time, let's say T is equal to 0, you started the heater, and it's like a step change, right? Then it start imparting the heat into the system, and for all future times, the heater is on. Fine, and other one is ramp, in the sense that, again, till T is equal to 0, there is no heat. Fine. Then after some time you switched on the heater, and but you did not step it up, but it's like a rate of, you fix the rate of change, in the sense that every minute, maybe every minute you are changing, let's say 5 degrees C. So it's like a linear increase, the ramp increase. And the last is, of course, pulse, in the sense that you just shook the system, you just switched on for some time, then switched off. So heater was on for some time and heater then later off. You switched it off. So now what I am trying to say is if you provide all these variable or all these possible inputs, the output response is highly different. For instance, if you're keeping the heat constant, so what is expected in this case? So let's say this is your Q and forget the fact that inlet temperature you're keeping it constant. So let's say if you're supplying a step input, what would be the output? Can someone say? So you are sending a step input to the system, and what would be the expected output? Initially, things were a steady state, and what would be the system? Intuitively, how the system would be responding? Can someone say? Anyone? Some feedback?
Sir, output will gradually increase.
So okay. Any more? Anything more you can say? So I'm talking about the step input. Huh? Any
Yes, sir.
additional or yeah. So you're saying its output would gradually increase. So any other thing someone can say? Any other contribution?
So like it will not be a sudden change in output.
Logically, what should happen? I just lost your sleep. Hello. Hello.
Yes, sir.
Yeah. Can someone? So you were saying something, Deepak. Then I saw.
Sir, the reactions will take time to create products, so the output will gradually increase. There will not be a sudden change like we have in input.
Okay, so that I agree, completely agree to that. And after some time, what do you expect?
Sir, then it will output will get saturated like the desired function
So you are
desired.
saying this is something like this.
Yes, sir.
Is this something like this? Okay, very nice. So this is something that is expected. Okay, so someone can think about RAM. What would happen? Can someone say, please? Anyway, so try to be more interactive. No, otherwise it's like very boring. See, in RAM, your output is gradually increasing. So you would really see that input is gradually increasing. So which means that your output will also gradually increase. There is no saturation as of now. And for pulse, as you expect, there would be a jump, step up and a step down. So eventually, what I'm trying to say is your system dynamics would highly dependent upon the input that is supplied. So these are some three standard inputs you could expect. There are other types of input also you may see. Other one is sinusoidal, which is quite unlikely that you would use because nobody would like to oscillate your operation. So sinusoidal inputs would generally tend to uh, oscillate your system a lot. So now what we are going to do, maybe in the rest of a few minutes, uh, considering these standard inputs, can we evaluate the output response quantitatively, not qualitatively? Now we say that okay, you might have an increase, then become saturated. So if you have a first order system model, which is this, and can we quantitatively express the output as a function of the input? So is this clear to you? So this is what we are going to do. Okay, so now let's check the step input. Step input, how do you define the step input? Step input is this, huh? It is many times, so let's say this is t is equal to 0 and this is 0 and let's say this is m. M is the magnitude of the step change. So generally the step inputs are defined like this. If there are, if so you switch on, it's like a switching on, right? Like switching on something. So till you switch us on, everything was 0. Then you switch on, then things got stepped up up to a magnitude m, which is something that you define. Okay, so the next one is and how, so see, we what is our transfer function? Y of s by u of s times k by tau s plus 1. The first thing to figure out what is y of t is figure out what is u of s. U of s, the transfer function of a step change is 1 by s if for a unit magnitude, and m by s if m is the magnitude of the step change. And this is quite standard. So step changes are there and happen when if there is a if you change the heat stop suddenly, sudden changes in the concentration and heat you change by changing electrical. So this is a very standard what you call input that you would really see in the system. Step inputs are always quite standard. Now we need to look at the ramp input. So RAM was our next example here, right? So we have to look at what is the what you call what is the context wherein you see a RAM response in the system. So basically, if there are drifting disturbances, uh, so let's say it's like this, right? Fouling happens. Fouling in a heat exchanger. So how what is fouling? So small initially when you install a heat exchanger, there won't be any fouling because it's fresh and new. Then over the time, okay, then there is mild scales might start form. Okay, then that scales would increase and it would start falling. So over that time, you would see a drifting difference. So maybe initially for some time you don't see anything. Then you would see there is some small change, so on and so forth. So let's say at time t is equal to 0, there is nothing, and afterwards it is your input is changing as a function of time alpha t, and the transfer function of input RAM responses what you call alpha by s square, where alpha is corresponding to the uh, slope. So see, a typical example is heat exchanger fouling. Catalyst activity. Catalyst would change, the effect of the catalysis would change with respect to time. Again, ambient temperature. So you see that over the time in the from morning to noon, maybe you see that the temperature would change. Sometimes ambient temperature is also modeled as a sinusoidal system because you would see nocturnal diurnal variation. It would generally see a jump and down, up and down. But if you could model it as a ramp system, even that is fine. But a typical example that you would really see is fouling, heat exchanger fouling, catalyst activity, because they would initially their effect would be minimal because when you keep a fresh charge of catalyst into the system, they would work perfectly. But over the time, yes, their performance tend to deteriorate. Okay, so now pulse. So pulse, how it works? So it initially there is no input, then stepped up for some time, which is known as for a time window known as pulse width. T is equal to 0, T is equal to PW. Okay. So then again we'll go to. And you can see that again in your Laplace transform table in the book, the transfer function of the pulse is this, or you can also derive it. How do you derive? You can assume that this is a step response. You can. So we have seen a similar example in the tutorial. So this is a non-standard function. So you will be able to split them as step up, step function, and a step down function. But pulse being a widely used function, you will be able to get the transfer function of that from the Laplace transform table that we have provided. Is there that is there in the book? For instance, let me show you. You see this. I hope you got a chance to look at your textbook. Are you looking at the textbook? Any of you?
Yes, so I saw this table in the book.
I couldn't hear you, Shruta.
Sir, I saw the Laplace transform chapter.
Hello.
I think it's the chapter number 3 or something.
Pardon me.
Hello, sir. I was saying that I saw the Laplace
Uh-huh.
transform part in the book.
Am I audible to you, or it's my problem? I couldn't hear.
So you
So,
are audible to us, but probably you are not able to hear us properly.
Okay. So, Visruta, what were you saying?
sir, I was just saying that I went through the book and I saw this Laplace transform chapter there as well.
Somehow, I don't know whether it's an issue with my end. I couldn't hear anything. Okay, so could you able to at least others? So can some could you able to look at the textbook? Are you able? Are you following the notes and text, or you're just following what I am teaching? Anyone? Can anyone say? Can any one of you give a feedback, please?
Sir, I think we have an appendix section in the book where these Laplace transformations have been taught briefly.
Yes.
So
Please,
looked
yeah.
at that,
Please
and it
keep it
was
ready
sufficient.
for by all practical purposes. We need this at every now and then. Even if you solve assignment problems, what you call exams. So it's like your logarithm table. So please keep it ready. If needed, take a Xerox and keep it ready for all your exercises. So from here onwards, you would be able to quickly convert a time domain function to Laplace domain and reverse, vice versa. So it may be a good idea if you practice and keep one copy of the Laplace transform table. You can of course look at your what you call appendix of the book. That's absolutely fine. But I think if you keep one ready reckoner copy for yourself. Okay. So let me continue. So this is also a standard thing. So basically, this is mostly would happen is your feed you switch off for some time. In a reactor, you would switch off the feed for some time, or maybe there is an interruption in the fuel. So you're working, your burner is working, then there is a shut off. So this is also quite standard scenario that you would encounter. So the transfer function of that is this. Okay, so now what are we going to, and again the last one is of course sinusoidal. Sinusoidal would have a frequency omega, amplitude A, frequency omega. So basically mostly for periodic and cyclic scenarios, maybe for, as I told, ambient example. So sometimes ambient temperatures are modeled as sinusoidal variations. Okay, maybe other example is electrical signals. Then let's say if you are using cooling water in an industry, because the cooling water is not really the cooling water, it is the water that is available at ambient temperature, so which is used for cooling. So the ambient temperature will have an effect on the water. So cooling water temperature would also vary with respect to time. Morning time, you would see that your heat transfer rate is very high, while post because if you wanted to kind of cool down the system, because your cooling water temperature would be very reasonably low, so that more heat transfer would take place, and that rate of heat transfer would keep on reducing when you move when the temperature is getting increased, and which essentially means that you are approaching noon and so on and so forth. So this is the time domain function a sin omega t for t greater than 0, and this is the Laplace transform a omega by s plus omega square for an amplitude a and frequency, angular frequency omega. So what again? So we are interested in calculating y of s as a function of y of s basically, and u of s is calculated because it would fall into one of this, or maybe I'm saying this is again candidate examples. You might, so let's say uh, this also could be an input, basically sawtooth. You should be able to develop a transfer function for this. This is like a sawtooth. You see, it's ramp up to some time, then it switches off. So you can write this as a function of two standard inputs, and you calculate the Laplace. Okay, so are you getting this? Are you comfortable with this? What I'm trying to say, are you able to follow it?
Yes, sir.
Perfect. So, so yeah, what I'm trying to say is, so we have looked at some standard forms, but you may be able to derive a non-standard form of this by combining a couple of standard forms. For instance, you would assume that there is a ramp up till here, then there is no ramp. So you can combine those two functions and get the inputs for those specific conditions. So now what we should do, now we should be able to, so u of s we could now characterize, now we should be able to get y of s. So just y, so getting y of s is quite easy. What you only need to multiply with y of u of s here. So that is not the thing. So y of s is just a multiplication of the transfer function, process transfer function with the input transfer function, which is we have seen. So in all the cases, if it is sinusoidal, it is a omega plus square omega square. Rectangular pulse means this. Ramp input being a alpha by a square for a slope of alpha, and for what you call step input, it is m by s for an amplitude of m. So step input is the transfer function of that is m by s for an amplitude of m. So now what we have to do is get y of s out of it. So we got y of s and go to y of t involved. Because eventually you would like to see how it is varying with respect to time, right? In the Laplace, things are okay. So let's see how it works. Let's take the simplest example, step input. So y of s is k by tau s plus k by tau s plus times u of s, and u of s m by s, right? And this would be your y of s. And how to get your y of t? So you will have to take basically a Laplace transform, then take the inverse of that. But I think for in your notes, step input transfer function is directly given. Otherwise, what you have to do is, okay, km, you take alpha by s plus beta by tau s plus 1. Then figure out what is alpha and beta and take the inverse. Is this clear to you? Any question? Any question? Okay, so sometimes for a step function, the what you call the direct Laplace inverse Laplace, you might be available in the it may be available in your table. So it would be easier for you to figure out. So Km would be the constant and 1 minus exponential of t by tau. So that's all about it. Uh, so how this responses looks like? How this response looks like? The response would be, you see, we can see how it works. So see, when t, so we have to look at t is equal to 0 to possibly t is equal to infinity, so that we can quantitatively characterize. When t is equal to 0 essentially means that so so yeah, so km times 1 minus. So we can see at what time. So this is, so here we are plotting as a function of t by tau. Okay, so when t by tau is equal to 0, which essentially means that initially there is no response, and when time tends to infinity, so or when this become large, so this term, so initially the whole term would so it would be like this 1 by infinity, and it would go to 0. Otherwise, this would keep on increasing and eventually it would saturate. This is what we have seen. And for first order system, one important property is that when t by tau is equal to 1, it means that t is equal to tau. At when time becomes the what we call tau, the process might have at least completed 63%, 63.2%. So this is like a characteristic. You can also say it for time t is equal to 2, but I think it is mostly characterized by t when time t is equal to tau, and this tau is called as time constant. So time constant is defined as when, if it is the time taken for the completion of 63.2 percentage of the overall time, overall. So here you see it is keep on increasing, and finally it becomes steady state. And but you see that 63.2 percentage of the what do you call overall time. So let's say this is 0 to 1, right? So at 63.2 percentage of the overall change will happen in tau time unit. If it is time in seconds, it is in seconds, minutes, it is in minutes, hours, it is in hours. So this is called as time form. Any questions? So this is something that you would keep on hearing every now and then. Any questions at the moment? You can actually calculate. So this is the way it works. So when t is equal to 0, you would figure it to be 0, 163.21, 2 tau 86, and finally it process becomes slow. 3 tau it becomes 95%, and 4 tau just becomes 98%, and 5 tau it will be close to 100%. If it is only for first order system plus step input, no other inputs would help. No, if you're sending a ramp input, this is not the response. First, this is the response of the first order system with step input. Again, example is your heater. Okay, you stepped up the heat duty, and the new temperature. This may be the temperature with respect to time. It increases and finally becomes steady state. This is your Q, heat with respect to time. Any questions so far? Any question? Is this all right to everyone?
Yes, sir.
Yes, sir.
Okay, so now we will also look at the ramp input, and we will possibly stop the figures. Perfect. So first order system with step input we have seen. Now let's see first order system with ramp input. Again, the transfer function for a slope of a, the transfer function would be a by s square. So y of s would be, so you have to substitute k by tau s plus 1 times a by s square. So it would be y of s become ka by s square into tau s plus 1. So this is of course not in your table because this is completely non-standard form. So what you could do is split them into partial fractions. So alpha by tau s plus 1, then s square become alpha 2 by s and alpha 3 by s square. So you will have to figure out what are those alpha, and you would see that ka by tau square is alpha 1, and ka is alpha 2, and again minus k is alpha 2 and ka is alpha 3. Please verify this. Of course, this is a very simple math, plus please verify by yourself. Okay. So, so it would be now, so again, when you take an inverse, it would be Ka by S square become Kat, and if you could combine this, eventually you will get K raised to K tau and you raised to minus T by tau minus F. And what you would see eventually, so here you see when T is really greater than tau, what would happen is this term So when t becomes close to, let's say, infinity is like a large number. So t is much less than tau, which may be close thousands or hundreds. This term eventually contribute less. So minus t by tau, that would eventually kind of become nullified, and what you would really see is this term would tend to dominate. Second term, which is k tau, because it's directly multiplied with time, and that would really mean that ka times t by tau would be the final final value of the response after some time. So if you so let's say if you try to plot its dynamics, so what you would really see initially, this factor might dominate, huh? That's what. Initially, this factor might dominate. So you would see a mild bend in the response. You would see. Look at it's like there is a mild bend. It's not straight line here. Then you would see it behaves like a straight line when t is very large. So you can also approximate it as a straight line. That's what we see here. You see the initial response. You would see a bend when both the terms would contribute, because exponential term would tend to play initially more, and after some time it would become flat. And this is the input profile UT by tau, and this would be your output profile. So any questions so far? So just to recap what we have done, looked at standard input, step, ramp, pulse, sinusoidal. Okay, then try to derive the outputs of first order system for step and ramp. So that's what we have done today. The next class we will look at sinusoidal input and how the response looks like. Then we will go to the second order system. And that's the agenda. So any questions so far? Any questions so far? Any questions so far?
No, sir.
So if this is all clear, I think you shall close the session today, and I'll be available for any doubt clearing between 1 and 2 as per our schedule. If you could log in, yes, I'll be able to. We can have a discussion and maybe hopefully see you here. Otherwise, we'll continue within the next Tuesday. Bye. Let's close the class.
Sure, sir. Thank you.